Hello and welcome to the 11th week of this course. In this week, we will study the relationship between compactness and completeness of metric spaces. We have already seen these notions before, and in this week we will see how they are interrelated. We will also study the set of continuous functions between two spaces as a topological space, and we will investigate the convergence of sequences and the behavior of functions under some of the topologies that we can put on this kind of space. So let us begin with the relationship between compactness and completeness in metric spaces. So remember that for a metric space XD, so this is just recalling things we have done previously. So recall. So for a metric space XD, we have first of all the notion of compactness. We have seen that metric space is compact if and only if it is sequentially compact, if and only if it is limit point compact. And in many cases, the sequential compactness is probably the most useful notion to use. We have also seen the notion of completeness. So completeness meant that every Cauchy sequence converges, and we have seen also the notion of a totally bounded metric space, and this was defined as well. You can also define the notion of a totally bounded subset of a metric space, and this was just that X has a finite cover of open epsilon balls for each epsilon width in 0. So given any epsilon, you can find finitely many open balls of radius epsilon which covers X. So now we will see some dependencies between these three notions. So first of all, it is quite easy to see. So let me denote this as dependencies or implications. So the first implication that we want is that compactness implies completeness. And this is because we can use, this is, as I said, this is equivalent to sequential compactness. And one can easily show that sequential compactness implies completeness. So why is this? So to show that a sequentially compact metric space XD is complete. So to show this, we take a Cauchy sequence, let's call it Xn in X, and it suffices to show that Xn has a convergent subsequence. So it suffices to show that Xn has a convergent subsequence. We proved this as a lemma when we were discussing compactness, that whenever you have a Cauchy sequence and it has a convergent subsequence, if every Cauchy sequence has a convergent subsequence, then the space X is complete. So we just have to show that Xn has a convergent subsequence But then by the sequential compactness, xm does have a convergent subsequence, as a convergent subsequence, and this means that x is complete. So compactness implies completeness. On the other hand, the converse is not true. Completeness does not imply compactness, and this is easy because as a counterexample we have Rn with the Euclidean metric. This is a complete space, as we have seen, is a complete metric space, but Rn is not compact. So we have that completeness does not imply compactness. Now the third one is that compactness implies that it is totally bounded. Now to show this, take any epsilon greater than 0 and consider the open cover. Consider the open cover of X with open metric walls, open epsilon walls, the of this type. So X is varying over the whole space X, but epsilon is fixed. So of course X is the union of all these epsilon balls because we are taking the union over all of X, and this means from compactness, this implies that X has a finite subcover of open epsilon balls from this open cover of all open epsilon balls. So this means that X is totally bounded. And similar to the completeness case, we can also show that the converse does not hold. So totally bounded does not imply compactness. So as an example of this situation, take the rationals in 0, 1, and I claim that so this is our X now with the subspace topology, and I claim that X is totally bounded. First of all, to show that X is totally bounded, let epsilon greater than 0 be given. Now take the open cover of X by open epsilon balls. So of the form BD Q epsilon for Q in the rationals in 0, 1, and of course X is again a union of all these open metric balls. And now I claim that this open cover BDQ epsilon also covers the set the space 0 1. So this is the open cover is taken from all the open epsilon balls with centers in the rationals in 0 1, and I claim that it also covers 0 1. And this is nothing but it follows from the density of the rationals, and this is because if you take any x in 0 1, then there exists a q in this set, such that the distance between x and q is less than epsilon. So this is from the density of q in R. And now this means that x belongs to the metric ball of radius epsilon and center q, and this means that x 0 1 is a subset of the union of these metric balls. And here also I should have said that x is a subset of this union. And now this means that you have that the space 0 1 has a finite subcover of open epsilon balls, which then implies that x has a finite subcover of open epsilon balls. And this step is from the compactness property of 0 1. And now this implies that x is totally bounded. However, x is not compact. It is not a compact set. And to see this, we will show that it is not sequentially compact. So not sequentially compact. And so we can construct a sequence of rational numbers in 0 1, so belonging to the set x, such that Qn converges to some irrational number in 0 1. So this is possible again by the sequential lemma, for example. And using the fact that Q is dense enough. So now that we have a sequence converging to an irrational number, this sequence Qn cannot have a convergent subsequence which converges to a point in X. First of all, if you have a convergent subsequence of Qn, then it must also converge to the irrational R, since any such convergent subsequence must converge to R, which is not in this set X, and R does not belong to X. So we see that X is not sequentially compact, and therefore X is not compact. So to summarize, we have seen that compactness implies completeness. Compactness also implies totally boundedness, but neither totally bounded nor completeness individually imply compactness. However, this is our main theorem for this lecture. So we have that a metric space XD is compact if and only if it is complete and totally bounded. So we see that when you take completeness and totally boundedness together, then it is an equivalent condition to compactness. So let's see a proof of this theorem, and this theorem, the proof of it has a very nice idea, and let us try to explain it in detail. So to begin the proof, we have already seen one way of implication, which is that compactness implies completeness and totally bounded. So we have to show the other implications. So suppose that X is complete and totally bounded, and we will show that X is compact, and in fact we will show that X is sequentially compact. Again, we will use the sequential compactness criteria. And to show that X is sequentially compact, let's begin with a sequence. So we will show that it has a convergent subsequence. So let Xn be a sequence in X, and we will show that Xn has a convergent. We will show that it has a Cauchy subsequence. It has a Cauchy subsequence, and this will imply that by completeness that it will have a convergent subsequence. Xn has a convergent subsequence. So we just have to find a subsequence which is also a Cauchy, which satisfies the Cauchy sequence criteria. So to construct a Cauchy subsequence of Xn, we will use the fact that it is totally bounded. So we have recursive definitions of sets. So let us start with the first step. So the first step lies in cover X by finitely many open balls of radius 1, epsilon equal to 1. So this is possible since X is totally bounded. Now, since X is so we have a finitely many open balls of radius 1 which cover X, and now we have infinitely many points Xn. So this is a kind of a pigeonhole principle. It says that if you have finitely many boxes and you have infinitely many things, and you want to put all those infinitely many things in these finitely many boxes, then one of the boxes must have infinitely many of the objects. So by the pigeonhole principle, so I want you to read up on it. If you are not familiar with this principle, it's quite intuitively obvious though. So there exists a ball, an open ball, B1 of radius 1, which contains infinitely many of the points xn. So it contains infinitely many points in the sequence xn. So in some sense, we can say that it has a the open ball B1 contains a subsequence of xn. And now let J1 be the indices of all the values of xn for which xn belongs to this open ball B1. So note that this is an infinite set. J1 is an infinite set. And now we are going to construct nested sequences of such infinite sets, and by considering uh, open covers of decreasing radii. So in the next step, step 2, cover X by finitely many balls, open balls again, open balls of radius half. And this means that at least one of the open balls in this cover of this one of the open balls, say B2, which is of radius half, contains infinitely many points of the set of the subsequence of xn precisely for the index set j1. So this is xn such that n belongs to j1. Okay, so we have that one of the open balls must contain infinitely many, because j1 is infinite. Since j1 is infinite and you have finitely many open balls of radius half, so we have that at least one of them must contain infinitely many points. And now let J2 be the set of indices such that xn belong to B2. And now we have a sequence of sets. So J2 is a subset of J1. So note that J2 is a subset of J1. And now in the step 3, we have a recursion. So suppose that jk has been defined. So this is the set of indices n in n such that xn belongs to some bk, where bk is an open ball of radius 1 by k. And again from jk we can define jk plus 1 by cover x by finitely many balls of radius 1 by k plus 1. And this means that there exists a bk plus 1 open 1 by k plus 1 ball such that bkk plus 1 contains infinitely many. Note that jk is an infinite set. Okay, so jk is an infinite set, and bk plus 1 contains infinitely many of the xn's such that n is in gk plus 1. And again we can define this is jk, and we can define gk plus 1 to be the set of indices such that xn belongs to bk, and we have that jk plus 1 is a subset of jk, and jk plus 1 is infinite. So this means that we have a nested sequence of sets, of infinite sets, j1 is bigger than j2, it contains j3 and so on, and in general jk contains jk plus 1. And using these sets now we can define a Cauchy subsequence, because because each of these sets jk is infinite. And so in this last step 4, we construct a subsequence x and k by choosing first n1, let n1 be in j1. So choosing a monotone subsequence, monotone. So monotone means it is increasing. So n1 less than n2, strictly increasing sequence of indices. So how can we do this? So first let us take any arbitrary index n1 which belongs to j1. Now choose n2 belonging to j2 such that n2 is greater than n1. And similarly, so this is possible because the set j2 is infinite. This is an infinite set. And in general, having chosen n1, n2 up to nk, choose nk plus 1 belonging to jk plus 1 such that nk plus 1 is strictly greater than nk. And now we have that the subsequence defined using these nks is a Cauchy subsequence. And this is simply because if so, to prove that it is Cauchy, so let us start with letter epsilon be greater than 0, and we have to show that there exists some n such that the distance of x n I and x n j is less than epsilon for all I and j greater than or equal to this capital N. And so we begin by choosing an n such that 1 by n is less than epsilon. So now choose capital N such that 1 by n is less than epsilon. And we note that for all I, j greater than or equal to capital N, we have that ni and nj belong to j capital N, since we have j capital N is a superset of jn plus 1 and it's a superset of jn plus 2 and so on. And also on the other side we have j1, j2 and so on. So if I and j are greater than or equal to capital N, then both ni and nj belong to this set jn. And this implies that the points x ni and x nj belong to this, well, let me write it here. So x ni and x nj belong to B capital N, and B capital N had radius, so this is less than, and this is less than the diameter of Bn, which is less than 2 over n. So in fact, I should here take not 1 over n, but 2 over n is less than epsilon. And so if we choose such an n, then this is less than epsilon. And this is true for all I and j greater than or equal to n. So this means that this subsequence x and k is Cauchy. And this completes the proof because x is complete and the Cauchy sequence must converge. So we have found a convergent subsequence.